Hello guys, this is Leo. Today I'll be going over particle kinematics in Cartesian coordinates. I'll start with a basic review of the coordinate system itself. I'll derive some equations of motion in this coordinate system. After that, I'll dive into an example of its application in 2D space, which is going to be related to aerospace engineering. And at the end of this video, I'll leave you guys with an exercise to think about in 3D space. A Cartesian coordinate system is basically a system where we have three perpendicular axes, x, y, and z, where x is pointing right, y is pointing up, and z will be coming out of the page by the right-hand rule in this case. Corresponding to the three axes, we will have three unit direction vectors, I, j, and k, or in the 2D case, only I and j, which are 1, 0, and 0, 1 respectively. With I, j, and k, we can essentially represent any vector in this kind of Cartesian space using a combination of them. For example, this yellow vector is 3 units left and 2 units down. We can write it as -3, -2, or equivalently, -3i plus -2j. Hopefully everything up to this point has been a pretty easy review. But the question is, how do we do kinematics in this kind of coordinate system? Well, what we need is to find a set of equations that describe the position, velocity, and acceleration of a particle in this coordinate system. By definition, the position is defined as x of t, I hat, y of t, j hat, and z of t, k hat, where x, y, and z are all functions of time. Now, to find the velocity, we can differentiate our position function with respect to time. And since the unit vectors are independent of time in this coordinate system, which is nice, we can just write the velocity as the time derivative of x, y, and z in the I, j, and k direction respectively. Acceleration is the derivative of velocity, so it's the second derivative of position with respect to time. In a similar manner, we can write down a of t as the second derivative of x, y, and z. Now, depending on the information that we have, we can choose to integrate a or v to get v or p, or choose to differentiate p and v to get v and a. As aerospace engineers, though, the thing that we care the most is probably none of them. It's the force. Force is the time derivative of momentum, which is ma plus m dot v. If we assume m dot is negligible, we would get the classic F equals ma equation. Now let's consider this. You see a plane flying through the sky on a hot sunny day where the surface radiation of heat is causing some turbulence to the flight, and you can see the plane is visibly undergoing some bumpy flight conditions. And you say to yourself, hey, I'm designing a plane too, so I don't want my plane to fall apart if it experiences the same kind of turbulence that this plane is experiencing right now. So the question that I have to ask myself is, how big is the force that this plane that I'm looking at is currently experiencing? To answer this question, we can probably first approximate a position function of the plane, which might look like this. I know this isn't probably the most realistic example that you'll ever see, but please just bear with me because it's only for the purpose of showing you guys some applications of kinematics. Now that we have our path graphed out, we can think of this as a particle kinematics problem in 2D. We can draw our x and y axes to define the frame of reference, and from there, we will have our position function, velocity function, and acceleration function shown as arrows that change with time. Now, mathematically, the position function may look like this. Taking the derivative of the position and then doing it again will give us velocity and acceleration. Assuming negligible mass rates, we can multiply the acceleration by mass to get our force. We can see that the force is actually a cosine sinusoid. Now we can graph force as a function of time. If we put time on the x-axis and the force on the y-axis, we can measure the maximum force that the plane is experiencing over this whole time of turbulence. And with higher masses, the maximum force is going to be higher given the same path, and for lower masses, the force is going to be lower. In real life, almost nothing can be accurately represented by a particle, sadly. But that doesn't render particle kinematics useless. In fact, engineers approximate all the time, and people have limited computation power. So, we as aerospace engineers can utilize particle kinematics during the initial design process to obtain a scientific estimate of high-level parameters or performance goals. So far, we've only talked about 2D, but what about 3D? Because that's the world we live in. In fact, in Cartesian coordinates, 3D kinematics is not too different in principle than 2D kinematics. We simply add an axis like we are doing in the video, and it becomes 3D. Looks pretty simple, right? It's time for your turn. Let's say we have a position function that's specified here, and the time goes from 0 to 2 pi. Let's say this is the position of a fighter jet in a spiral climb. My question for you is then, what is the acceleration during this whole maneuver, and what is the force that's on the aircraft? Give it some thoughts if you're interested, but otherwise, this would be the end of my video, and thank you for watching. Here is the reference link to the image that I used in this video, and by the way, this video is created using Manim, M-A-N-I-M, which is an open source Python library for making animations like this. I would also leave a link in the discussion board to my code that's used to create this video. If you're interested, you can take a look, probably install Manim and see what wonderful things you can come up with.